Let's start. So a rock and a pond. Remember how Andrew said, well, I don't need to draw a drawing because there's a drawing in the book. Well, don't have that attitude. You must make drawings. Look at example number one. Okay, I threw a rock in a pond and I make a circle, but the circle is going outward, right? The circle is getting bigger and bigger. You guys okay with that scenario? Okay. The radius of the outer ripple increases at a constant rate of 1 foot per second. At what rate is the total area of the circle increasing when the radius is 2 feet? Draw a picture and name the variables and constants, particularly the rates. Anything that's changing can be called a variable. Things that are not changing must be named by their numerical constants. Don't ever call anything a constant by a variable, and don't ever call anything that's changing make it into a constant where it isn't changing. Things that are changing get to be variables. So for example, the radius of this circle, is it a constant or is it a variable?
Variable.
Yeah, because the radius is changing, so it's a variable. I'll call it R. R for radius, okay? It also wants me to name the rates. At what rate is this radius changing?
1 foot per second.
1 foot per second, right? So the rate of change of the radius with respect to time is 1 foot per second. So you're going to call that dr dt. That is the change in r over the change in time is the rate at which the radius is changing. Change of rate over change in time. But I just want to remind you, the change of rate over the change in time, that tells you the rate at which the radius is changing. But if we take the limit as delta t approaches 0, then all the deltas magically turn into d's, and we've got our dr dt. Okay? At what rate is the total area of the circle increasing when the radius is equal to 2 feet? So maybe off here, if you want to put radius equals 2 feet, that's fine. But you know, you're going to have to keep r a variable because it is changing. So there it is. I did step 1. Step 2, write down the numerical information. Well, if you did step 1 right, your step 2 should be fine as well. And then step 3, what are we to find? They want the rate at which the total area of the circle is increasing, right? So they want me to find dA dt. That's what they want me to find. And make it very clear to yourself what it is they want you to find, because that's going to determine what equation you write down, what they want you to find. Now it says write the equation that relates the variables. Don't plug in any numbers yet. Well, since it's dA dt they want, I'm going to have to get an equation with area, pi r squared, okay? Now, if I plugged in a radius right now, I'd get area equal 4 pi. What is that telling me?
The area is 4 pi.
Yeah, thank you very much, Andrew. I couldn't have said it better myself. That the area is 4 pi. And hey, that's all well and good, but they're not asking for what the area is at this point in time. They want to know the rate at which the area is increasing. So before you plug in any numbers, you're going to have to take the derivative, and specifically, it's an implicit derivative with respect to t. So that's your next step. You're going to get dA dt on the left side. You're going to take the implicit derivative with respect to t. Take the implicit derivative with respect to t of both sides of the equation. And now when I take the derivative of r is a variable, so the derivative of anything squared with respect to d is going to be 2 times that thing, right? So I got 2 dA dt equals pi times 2r. But then because this r is not the same as that t, I'm going to have to do chain rule. So the derivative of whatever squared is going to be 2 times whatever times the derivative of whatever with respect to t. And as always happens with implicit derivative, as often happens with implicit derivative, you end up sprouting at d whatever. You know, dy dx when we were learning implicit derivative, now it's dr dt. Before I go on, any question or issue on this?
It turns out to be 4 pi.
Why don't you just make it 2 pi r?
Oh, I don't know. Omar asked, why don't I make it 2 pi r? You can do that if you like, because we're you know, free to do that. The Constitution assures us that we can write our quantities in any order we want. Okay, at this point, we're down to step 6. Hey, solve for what you want and evaluate. So I'm going to get my expression for dA dt. And this is going to be, I'll do it Omar's way, 2 pi times 2 feet times dr dt, which is 1 foot per minute. Okay. Oh, it's 1 foot per second, excuse me. 1 foot per second. And now you'll notice even the units turn out okay. I would expect a rate of change of area to be square feet per second, and that's what I get, square feet per second. I get dA dt equals 4 pi square feet per second. I substituted a 2 feet for the r because r is equal to 2 feet at that point in time. Yes?
Remember when you said if you plugged it in, you find the area,
Yes.
and then it would have been 4 pi, and then the answer is 4 pi?
But that's a coincidence.
Yeah, I know.
Isn't that
was
weird?
funny.
So yeah, interesting coincidence. So let me ask you guys this question. What if I said, hey, I don't want the rate of change of the area when r is 2. I want the rate of change of the area when r is 6 feet. That is, I'm going to wait until my little circle is like this, and then I'm going to get dA dt. Well, you tell me, is the rate of change of the area going to be smaller, bigger, or the same when r is 6? Daniel, why do you say bigger?
Because that you want to use 2 and the derivative of the area, you use 6.
Okay, so Daniel's going, hey, look at the numbers, look at that algebraically. Instead of a 2, I have a 6. This is going to be 3 times bigger. Is anyone thinking conceptually in terms of the circle itself? Why am I getting more area per second once the circle's gigantically huge?
Because a little bit extra.
Go ahead, Leilani.
Because you're increasing the r by 3, but you have to square it, so that would make it into 9 rather than just 4.
Okay, but I'm trying to get to something else here. Here, when your r moves out a little bit, your circle goes to here, and so this extra area is the rate of change of area, you know? That extra area is telling you the rate of change of area. Well, what if you're way out here and then your radius increases a little bit? Do you see that that extra area now is much, much greater than the extra area was when the radius was 2? You know, this is a way bigger, this annular ring has way more area than that annular ring. So I want you to also be thinking conceptually, hey, does it make sense that if my r was bigger, my dA dt would be bigger? And the answer is yeah, absolutely. I mean, look, you know, it'd be like if you bought a pizza. If I got an 8-inch pizza and the guy said, hey, I'll give you an extra inch, I'd say, okay, that'd be great. But if I got a 14-inch pizza and he said, I'll give you an extra inch, I'd say, yeah, that's great. As long as it's not all just crust, you know. Okay, well, hey, please read number 2, because we're done with this problem. Please make a drawing of this situation. I'll get you started. Here's the guy. Please make a drawing of the situation and label the drawing. I want to see what you guys get. I'm going to walk around and help you, quote unquote. Label the drawing. Give me your distances and angles and all that good stuff. Label variables, which are variables. Yeah, you're going to have to use a separate sheet of paper probably. I crammed everything onto one side of the sheet of paper here, so yeah, good for you, actually. Good looking loom there. Make sure the string is a wiggly string. Don't make the string just straight. I mean, and your balloon has to have a string. Yeah, good looking balloon there. Where's your drawing? Oh, there it is. Oh, good for you. Oh, so you have a gondola on your balloon. Good for you. I was picturing a kid's balloon. Sandra has like a higher blue. And that's fine. Okay, so far so good. Copy that drawing, label that drawing. Good. Good for you. Okay. Does this angle get to be a variable? Is it changing? Then yes. And make sure your angle's a variable because it's changing. Your angle, I mean, yeah, it has the value of whatever they say, but it's changing. It's a variable. So call your angle a variable. Did you call your angle a variable? Call it a variable. Give it a name. You call it theta. Good for you. You call the angle theta. Okay. I'm gonna have a balloon on the screen. Okay, guys, I'm gonna show you now, and there's a couple of really important points I wanna make. First of all, this distance, the distance between me and where the balloon was released, does that get to be a variable or is it a constant?
Constant.
Good for you guys, that's not changing, that's 500 feet, and that's not changing. Great. Let's keep going. The balloon is rising at an angle of elevation of pi/6, which is 30 degrees. Is this angle get to be a constant? Is it a constant or a variable?
Variable.
Yeah, because it's changing. So call it theta. Sure, theta is equal to pi/6 radians at this point in time, but it gets to be a variable because he's changing, okay? And they want to know, well, the angle is increasing at 0.23 radians per minute. So are you okay that that's giving me d theta dt? So somewhere, right, d theta dt equals 0.23 radians per minute. How fast is the balloon rising? So what other dimension am I going to have to label here?
Height.
Good, the height, I need to know. And this height, is it a because, I mean, I could find what that height is, right? It ends up being 500 radical 3, because this is a 30-degree angle. So that's 500 over radical 3. But should I call it 500 over radical 3, or should I call it a variable?
Variable.
Absolutely, because your balloon's going up, its height is changing. Sure, at this point in time, the height is 500 over radical 3, because at this point in time, this is a 30-degree angle. But theta and h are changing. Okay, it is now time to get an equation relating those variables. What equation would you like to get?
H equals 510A, or 10 theta.
Okay, Abigail, what were you saying? Okay, tan theta equals h over 500. What were you saying?
Oh, I was already solved for H.
Oh.
It's the
okay,
same
that
thing.
way.
I
Oh,
just
okay,
solved
good for
for
you
H.
guys. Okay, you guys okay with that? You're going to do tangent theta equals h over 500.
Yeah.
Good. What if instead of this guy being 500, what if it ended up that the hypotenuse was 500? Then what would your equation have been?
Sine.
Theta.
Yeah, sine theta. So you do have to look at the drawing to make this determination. Then let's go ahead and get the implicit derivative. So I'm going to get the derivative of theta, the derivative of both sides of the equation with respect to t. So I'm going to go d dt, the derivative with respect to t. So I'm going to be sprouting d theta dt's and dh dt's. So I got secant squared theta d theta dt equals 1 over 500 times dh dt. You guys okay with that? Okay, sorry about that. Okay. They want dh dt. So I got 500 times secant squared theta. This theta is 30 degrees, right? Pi over 6. So I just need to know what the secant squared of pi over 6 is. Secant is 1 over the cosine. The cosine of pi over 6 is rad 3 over 2. So the square of that is going to be 3 over 4. d theta dt, they tell me, is 0.23. And this is radians per minute. By the way, trigonometric functions are unitless. Sine, cosine, tangent, secant, cosecant, cotangent, they're all unitless. And this 500 though, that 500 was 500 feet, right? 500 feet. And then this equals dHdt. But one thing that's weird, and I don't know if I taught it to this class, but degrees and radians are both unitless quantities. Like a radian is just, a radian is a ratio of the arc length over the radius of the circle. Where here's the radius of the circle, and this is the arc length, and this is the angle theta. And so S over R is just a ratio, so it's unitless. So radians are actually a unitless quantity. So I end up with the product of those guys. And the units are going to be feet per minute. 500 times, so 5.
Mr. Shana,
Yeah.
is this supposed to be 4/3 because it's flipped?
Yes, yes. Thank you. Thank you, Zach. It's 4/3. By the way, you're going to actually get some problems where you won't know what theta is, but you're going to be asked to get the cosine or sine of theta, and you're only going to be able to get that by using the lengths of the sides of the triangle. You won't even know what theta is, but you'll be able to get what the sine of theta or cosine of theta is anyway. Thank you, Zach. 500 times 4 divided by 3 times 0.123. So I get 153 feet per minute equals dHdt. So you guys okay with that one?
Mm-hmm.
Make your drawing, get your equation relating the variables, take the implicit derivative, and then plug in. Hey, please read example number 3. And then make a drawing of it on a separate sheet of paper because there's no room on your sheet.
Is 2 over radical 3, and then you square it. So it's x squared. Oh, I love that. This is my favorite one.
Go ahead and label the ladder, and let's see what you come up with. I'll give you a minute. I want to see if you guys can label this ladder, label the variables and constants of this ladder, and see if you can figure it out.
Mr. Shana.
Yeah. Wait, let me see this.
That's the coefficient of friction.
Okay, who gets to be variables and who gets to be constants in this drawing? Good for you. You know that that's a constant, that's for sure. Good for you. Good, everyone's getting the constant correct. That makes me happy. Good. Good looking ladder you got there. Yay, you figured that out. You figured everything out. Good. Okay. I gotta tell you, I made looked at a representative sample, and everyone seemed to be doing okay. The length of the ladder, variable or constant?
Constant.
Constant. That's not changing. It's a 10-foot ladder. Okay. They tell me it's 6 feet to get away from the house. But tell me, is this guy going to be a constant or variable?
Variable.
Yeah, variable, because it's moving. So how many people called that X? Okay, good for you. Did anyone call it something else? What'd you call it?
B.
B is fine. Whatever you want to call it is fine with me. Base and height, huh? So how many people call this length y? Okay, good for you guys. Well, that's what we got. And at this point in time, is x is equal to 6 feet, but I know it's moving, and in fact, they tell me that the base is moving that way. dx dt is equal to 2 feet per second. And they want to know how fast is the top of the ladder moving down the wall. So they want to know what dy dt is. So tell me, what's an equation that relates x, y, and 10?
Pythagorean theorem.
Yeah, Pythagorean theorem. Good. Hey, let's just crank through this one. X squared plus y squared equals 10 squared, right? And so now I'm going to take the implicit derivative of both sides of this equation. You'll notice I'm not really trying to do any substitution. I don't really need to. So I got 2x dx dt plus 2y dy dt equals 0. I got to solve for dy dt. So I got dy dt equals negative 2x dx dt over 2y. So let's plug in. This is the part I think that's easy. X is 6. Negative 2 times 6 feet times dx dt, which is 2 feet per second, over 2 times y. And what's my y? If this guy's 10 and this guy's 6, what's my y?
8.
8. Good. Do you guys know your Pythagorean triples? So that would be 8 feet. So I end up with, what do I even need my calculator for? 12 over 8, what is that? 3/2. But one of the feet cancel and I get 1.5 feet per second. But please note, it's negative. What does it mean for dH dt to be negative 1.5 feet per second?
Sliding down.
Yeah, it's sliding down. Y is getting shorter. Y isn't getting bigger. X is getting bigger, so the rate of change of X is positive because X is getting bigger. Y is getting shorter. So dy dt is going to be negative. Any question or problem on that third example? Look at part B. Now I want to know the rate at which the area of the triangle formed by the ladder is changing. What equation am I going to have to do now?
Area equals 1/2 x times y.
Yeah, area equals 1/2 xy. Good. And then when you take the implicit derivative, okay, you're going to have to do product rule. You're going to have to do the derivative of the first times the second plus the first times the derivative of the second. And I just want to show you that right now. For part B, you would need to do product rule. And you'll do the implicit derivative with product rule. So you got dx dt, dy dt. That's part B. All right, as we zippity-doo-dah through these 5 examples, it looks like many of you know what you're doing, and that's good. If not, just use these examples as a guide. Let me show you number 4. And it's something that I need to show you, because many of you may have forgotten how to do a problem like this. I've got a conical tank with the vertex down, and it's draining at a rate of 10 cubic feet per second. What quantity is that? What rate of change is that if it's 10 cubic feet per second? Volume. Yeah, volume. Hopefully you're seeing that they gave you the rate of change of volume. And they tell you it's 10 cubic feet per second. But please notice it's draining. So what is my dV dt actually going to have to be?
Negative.
Good, negative 10. I'm losing volume here, right? I've got some liquid, but I'm losing it. So that's negative 10 cubic feet per second. They tell me the height of the tank is 8 feet. and the radius of the tank itself is 6 feet. And they tell me where is that? When the height of the fluid is 5 feet. So this distance from there to there is 5 feet. Okay? And they want to know the rate of change of the height of the fluid.
You have to find the ratio.
That's correct. So tell me, they've given us dVdt, they're asking for dHdt. What formula am I going to have to start with? Hopefully you're thinking volume.
Yeah.
You're not going to do surface area or anything freaky like that because they gave you dVdt. So you know you're going to have to start with volume. Volume equals pi r squared h. Now, here's the problem. If I took the implicit derivative of both sides of this equation, it would look like this, and I'm going to put this in braces. It would be dV dt equals pi times the derivative of the first, 2r dr dt, times the second, plus the first, r squared, times the derivative of the second.
Mr. Shannon?
Yes.
Isn't that the formula for a cylinder though?
Oh, yeah. I blame my illness. I blame NyQuil. Thank you. Who said that, by the way?
Justin.
Thank you, Justin. Thank you very much. Yeah. Thank you. My bad. Now everyone in YouTube land will see me making mistakes. But here's the point I want to make, okay? This is fine. Everything I wrote here is totally wonderful, except for one thing. I don't know what dr dt is, and I don't care what dr dt is. So I've got an equation with two unknowns, right? I don't know what dH dt is, that's what they're asking me to find, and I don't know what dr dt is, and I don't care what dr dt is. So I can't just keep it like this. I can't treat this like this problem where it was all good. It was okay to have two of these rates on the right side of the equation on this problem because I already knew one of them. I knew what dx dt was, and I could find what dy dt was. I knew dx dt and dy dt, didn't I? I knew them both, so I could find what dA dt is. But here, I don't know what dr dt is, and I don't care what dr dt is. And so when that happens, this is a situation where you're going to want to substitute for one of the variables. And I've got a ratio, and this is the part I had to show you. I've got similar triangles here. I've got a ratio, radius to height is 6 to 8, and that's never going to change. No matter what triangle I choose, I'm always going to have similar triangles. So if I call this guy R, and that height is 5, then I hope you see that the ratio of 6 to 8 is going to equal always the ratio of R to H. If I call that R and I call this guy H, okay? That ratio is always going to be true, which means 3/4 H is equal to R. And you're going to have to make that substitution here because you only want H's in your equation. You don't want R's. You don't want to get the derivative of dr dt. You don't want to try to figure out what R is in the first place. So you're going to make this substitution. So when you get one of these problems, remember to make that substitution. So I got v equals 1/3 pi times 3/4 h squared times h, or v equals 9/16, so that's 3/16 pi h to the third. And now I'm happy because I've got an expression of v only in terms of h. I don't have any r's in there, and that's good, because I don't know what r is and I don't care what r is. Now let's go ahead and do my dv dt equals 9/16 pi h squared times dh dt. And at this point, I'll just say etc. You just plug in and solve for dh dt. By the way, is dh dt going to be positive or negative?
Negative.
Good, it's going to be negative because my dv dt is negative, and that makes sense because my height's getting smaller. Any question or problem on the conical tank problem? And you'll get one of these tonight. And I just want you to see that occasionally you are going to want to make that substitution to simplify the right side, so there's only one variable instead of two, so you're not doing that product rule thing. But, oh well. But example 5, if you look at example 5, you do have to do the product rule on example 5. Area equals length times width, and so dAdt on example 5 is going to be PL dt times W plus L times dW dt. And it's all good because just like this, you've got dL dt and dW dt, so it's all good, you know. So sometimes you don't have to make a substitution, but sometimes you do. Good luck, you guys.